So in this video I'm going to take a look at problem 30 from chapter 25. So here we have a hollow cylinder with some inner and outer radius given. So this part is material, but inside there is a hollowed out the cylindrical part, and we are given the inner and outer radii to be R1 and say R2, and we are also given the resistivity of this material, and they're asking for the resistance of this whole construction if the current is flowing from inside to the outside. So we have this hollow cylinder, and current is somehow flowing from the inner surface to the outer surface. Yeah. So this is the problem. In fact, they're asking us to show that this is equal to some particular expression given in the problem. And the length of the cylinder is given. And this is a level 3 problem, so it's going to be a little bit involved. So it does contain an integral, so I think that's one reason for difficulty. But other than that, this is the hard part for this problem is the visualization. So how do you start a problem like this? Well, they are giving you resistivity and the geometry of the object that you're looking at. So it suggests that you're going to use, this is going to be an application of this formula. Right? So for a given, let's say a rectangular piece of resistance, given its resistivity, its length, and the cross-sectional area, you can calculate its resistance this way. Now, is this applicable here? Now, for that to be applicable, all these quantities need to be well-defined. Yeah, so this L, the length over which the current is passing, should be well-defined. This area, the area over which your current density flows through, needs to be well-defined, and the resistivity needs to be well-defined. Okay? If that doesn't work, then you have to somehow separate your resistive element into little parts, and then figure out if they are connected in series or in parallel or something perhaps more complicated, and figure out the equivalent resistance. Right? Now this one is not directly applicable here because, for one thing, if the current is flowing from inside to the outside of this hollow cylinder, the surface area is not going to be well defined. Inside it's flowing through a cylinder of small radius. Outside the radius gets larger and larger, so the surface area gets larger and larger. Right? The surface area in this case is going to be the circumference of the circle times the length of the cylinder. Okay? So that's not constant, so the area is not well defined. We have to divide this into smaller parts where this formula is going to be directly applicable. Now, how do we do that? Well, I think the easiest way, the way that suggests itself, is to divide this into little cylindrical shells. Okay. So I'm going to have these cylindrical shells that extend beyond the length of the cylinder itself. You can do this more complicated. You can also divide the cylindrical shell into rings, and those rings into little pieces, and so on and so forth. But for the cylindrical shell, as we will see, the formula is going to be applicable. And the current is flowing from inside to the outside. So the same current is going to pass through all these cylindrical shells, which means all those resistors are in fact connected in series. And for the series connection, we simply add up the resistances. So our total resistance is going to be just some of the little resistances of those cylindrical shells. And each of those little resistances, the cylindrical shell, the resistance of each of those cylindrical shells is going to be dr rho. This is constant all over the thickness of the shell divided by the area of the shell. Okay? So this is a constant, this is not a constant, and this is our how we are going to go from inner part of the shell to the outer part. So we choose some coordinate system, something like a cylindrical coordinates where the z-axis is coincident with the axis of these cylinders. Then that is going to be just the radial direction. Okay, this dl is going to correspond to dr. And the area, as I said, is going to correspond to the circumference times the length of the cylinder. So let's do this more explicitly. So this is my r. So I'm trying to take this r from r1 to r2. So this integral is in fact going to correspond to r starting from r1 to R2, that rho is a constant. I can just write this. This dl corresponds to moving in the radial direction, so that is just dr. And this A is the area of the cylindrical shell that I am currently dealing with, and that is going to be 2 pi r, the circumference, times the length of the cylinder. Okay. And now this is an integral, it's a definite integral. You can take this, this rho, 2 pi and L, they're all constants, you can take them out. The integral of 1 over r is logarithm of r, and this is going to be difference of two logarithms that corresponds to the ratio of the logarithm of the ratios. Okay. So let's take the constants out, rho over 2 pi L, and we are going to have difference of logarithms, which is the ratio, a logarithm of the ratios. Right? I mean, you could, of course, do this more elaborately when you're taking the integral, if you're not sure what you're doing. But the expression is already given in the book, and this is, in fact, the same expression that they are giving us. So this is how you reach this answer. This was part A. Now, for the part B, they are giving you some values for a particular resistance that's made of carbon. The inner and outer radii, and so you just need to plug numbers in. I'm not going to do this part. And then they're asking, what is the resistance in the part if the current is flowing parallel to the axis? So if you connect, for example, a battery like this, right, to two sides, of course, again, it has to start uniformly from this side, so maybe a connection just to one point is not going to work. But, you know, you can introduce some additional connections over there, but now the current is flowing this way. So initially, for the part A, the current was flowing sort of radially from the axis to the outside, from the inner shell to the outer shell. Here now it's flowing along the axis. Right? Now again, the first thing you want to try for this part is going to be this formula, because again you are given the geometry and you're given the resistivity and so on and so forth. And again, you need to question whether this is directly applicable. So is there a well-defined resistivity? Is there a well-defined length? Is there a well-defined surface area? In this case, it turns out that it is applicable. Right? So the resistivity is constant. It is certainly applicable. This length is a well-defined length. You're just moving current over some length of the cylinder. And then the surface area, if you divide this into little parts now this way, if you just imagine there are some cylindrical shells of this thickness, let's say dl, then each of these are going to have the same surface area. They're all the same, so you might as well just think of this as one. Okay? You don't need to divide this into some drs and try to figure out what the integral of those little resistances are going to be. So this is very, very similar to a situation where you have like a cube. So you're trying to go from one side of the cube to the other. You connect a battery, and you don't need to divide this cube into parts. If you know the length of the cube, and if you know the surface area, then you can just calculate the resistivity using that formula. The same thing here. Different geometry, but ultimately, because the area is constant and L is well defined, you can actually apply this. So what is left to us is to define that area. L is already given, so this is going to be rho L, and our area is going to be the area of the bigger disk, pi r2 square, minus area of the smaller disk, pi r1 square. Okay. You can obviously simplify this a little bit further, but essentially the answer is going to be